Our next lesson is about the angle-angle, or AA, the side-side-side, or SSS, and side-angle-side, or SAS, criterion for similarity. In this lesson, we'll cover two CCRSM standards to use the properties of similarity transformations to establish the angle-angle criterion for two triangles to be similar. And the second is to use congruence and similarity criteria for triangles to solve problems and to prove relationships in geometric figures. Let's get started. Lesson 15 is about the angle-angle criterion for two triangles to be similar. Now, before I get into the AA criterion, I want to kind of go back to Module 1. And in Module 1, we talked a lot about congruence in terms of rigid motions. We define congruence to be a sequence of rigid motions that map one shape onto another. And then eventually we said, well, instead of showing a sequence of rigid motions, I'm now, for triangles, going to take a shortcut, and instead of talking about rigid motions, I'm going to talk about the side-side-side, the side-angle-side, and the angle-side-angle criteria for triangles to be congruent. Now, we're going to follow the exact same path in this module, except instead of talking about congruence, we're going to talk about similarity. And instead of talking about rigid motions, we'll talk about rigid motions and dilations, which together are called similarity transformations. Now, today we're focused on this piece. Instead of showing a sequence of similarity transformations, meaning rigid motions and dilations, I'm now, for triangles, going to look at ways that we can use sides and angles to show that triangles are congruent without showing the similarity transformations. And specifically right now, we're looking at ASA, which in similarity, we don't need the side because you can't use one side to be proportional. This will become the angle-angle criteria. Now, I'm going to draw some pictures, and if you want to follow along with your student materials, I would use the page before this. There's a blank page up here that you can use. And I want to remind you that we started this unit by talking about dilations. And so if I have a triangle, and for simplicity, I'll use this point as the center of dilation. I'll call this point A and B. And using, let's say, the ratio method with a scale factor of 1.5, I can dilate point B by a scale factor of 1.5 to be roughly here. We should draw the dotted line first, and dotted line. And then dilate point A roughly here. And we have proved, using the side splitter theorem, that these lines will be parallel. Okay? Think about the black triangle and this big red triangle. Now, we in Module 1 talked a lot about parallel lines and properties we get from parallel lines, and we talked about corresponding angles. That these two angles, angle OAB and angle OA''B', are congruent because they're corresponding angles. And similarly, this angle and this angle are also corresponding angles, and they're congruent. And finally, O is congruent to itself by the reflexive property. And so these two triangles here, we've already proved that they are similar, but they also have the property that all three angles of one triangle are congruent to all three angles of the other triangle, which is a property which happens in similarity. Now, below this, you can draw this picture. I'm going to go to a Smart Notebook file so I can use some things with it. But below this picture, you can draw this next picture. Now, the standard says to use the properties of similarity transformations to establish the angle-angle criterion for two triangles to be similar. So the same way that we established it for congruence, I'm going to show you a sequence of rigid motions and dilations, meaning some similarity transformations that will map one onto the other. The first step you can do is you rotate one of the figures so that all the corresponding sides are parallel. And by the way, if you can't do that, then it's likely that the two shapes are not going to be similar to each other. Now, the second step is to draw a line between the corresponding points, so between A and A prime, between B and B prime, between C and C prime, and those lines will be concurrent, and the point of concurrency is the center of the dilation. And so those points will be concurrent, and this is the center of dilation, and I could do a dilation to map one onto the other. So that's the series of rigid motions you could use for shapes to show that they are similar to each other. Now let's go back to the student materials on page 96. Back in our student materials, a really important question is asked in number 3. Why is it that you only need to construct triangles where 2 pairs of angles are equal and not 3? So far in this video, I've talked about 3 angles of one triangle and 3 angles of the other, but the truth is you only need 2. And the reason you only need 2 is because the third angle is always going to be 180 degrees minus the measure of those 2. So in other words, if you have angle 1 and angle 2, then I know what the third angle is going to be because I subtract those 2 from 180. One quick example, if I have a triangle, and this is, let's say, 60 degrees, and this is 70 degrees, I know what this angle is going to be. I know it's going to be 50 degrees just by knowing those 2. And for those exact same reasons, I can get by with angle knowing 2 angles and not all 3 because the third angle is determined by the other 2. Now, one example of the angle in practice is on number 7. Are the triangles shown below similar? And explain. If the triangles are similar, identify any missing angle and side length measurements. Well, I'm given this angle is the same as this angle. So that tells me something, but I don't know if this third angle right here is the same as this angle down here, because it's obviously not these two. So I can find this angle by adding 44.24 and 57.12. And that third angle is 78.46 degrees, which sounds really familiar. That's what it is over here, which means that by the angle criteria, that these two triangles must be similar. And for the sake of time, I'm going to move on and not worry about finding the missing side lengths. Let's go now to lesson 17. Lesson 17 is about the SAS and the SSS criteria for two triangles to be similar. Now we've defined similar to be there's a series or sequence of rigid motions and dilations or similarity transformations that map one onto the other. Just like I showed earlier with angle, if you do a rotation and then a dilation, that's the series of rigid motions that you can use. Okay, now we can use SAS and SSS, and let me give you a few examples of what that looks like. We'll first do exploratory challenge 1, exercises 1 and 2. So examine the figure, and we'll notice that this length right here is 4, and this is angle A, and this length is 3. This length right here is 9 plus 4, or 13. I have the exact same angle by the reflexive property, and this length right here is 9.75. Okay, hopefully you can see this small triangle, which is in green, and the big triangle right here, which is kind of in blue. Okay, now I see a side, the angle in between, and a side. And so if these were similar, then it would be by the side, angle, side similarity criteria. But I do have to check that these two sides are proportional. So let me check that 4 divided by 3 is the same as 13 divided by 9.75. And you can check that by dividing both of them or by cross-multiplying and seeing if you get the same number. I'm going to divide these. 4/3 is 1.3 repeating. And 13 divided by 9.75 is 1.3 repeating. And so, yes, they are proportional. And so these two triangles are similar by the side, angle, side similarity criteria. Let's next look at number 2. So again, we will look at the figure, and hopefully you see a side, an angle, and a side, which is 13, an angle by the reflexive property, and a side that is 9. So if these are similar, it'd be by the side, angle, side similarity criteria, but we must check the sides. So I'll look at 3 divided by 2, and that is, left to top. Is that similar to 13 over 9? And I'll divide them. 3/2 is 1.5. And 13 divided by 9 is 1.4 repeating, which are not the same, and so they are not similar. Next, I want to go to number 3, which is about the side, side, side criteria, because I have all 3 sides of one triangle and all 3 sides of the others. So examine the figure and answer the questions below. I just want to look at these to see, are they similar? And the trick to this is matching up the corresponding sides. And I like to look at the small one with the small one. And I'm going to do a left triangle to right triangle ratio. Is that the same as middle to middle? Again, it's left to right. And is that the same as big to big? Left to right ratio. Now, I notice that this is 2, and this is 2, and this is 2, and they're all the same. So the answer is yes, they're similar by the side, side, side criteria. And just so you know, the way we write that, using the correct notation, is triangle ABC is similar to triangle. Now, A corresponds with, A prime, and B corresponds with B prime, and C corresponds with C prime. Okay, let me see, by the SSS similarity criteria. All right, this video is about the angle, angle, side, 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 and side, angle, side criteria for similarity. Thank you for watching.